Alright, so picking up where we left off, last video, we spent some time going through the first 5 rules for building Lewis structures, which is going to get us a lot of places, but sometimes within we have to account for different ways of drawing it, okay? And I also taught you guys how to calculate formal charges. So this video, we're going to go through how to use the formal charge to then differentiate between possible structures to decide which one's better, if one is better. And then the next step down is, what if formal charges doesn't give us enough information to decide which one's better? Is there another way to tell? Okay, so we're going to use silicon dioxide and the cyanate polyatomic ion to go through that. Stupid phone. All right, so we'll start over here with silicon dioxide. All right, so we're going to start this off just like we always do. Still, again, making sure you guys have your set of rules. We're always going to start way up there with step 1 and work our way down until we've come to a satisfactory finish. Okay? So step 1 is still identifying the number of valence electrons. So silicon has 4. I've got 2 oxygens. That's going to give me 16. I don't have any charges up there to worry about. Okay, so I've got 16 valence electrons. Now, silicon has a lower electronegativity, so that tells me that silicon will be my central atom. All right, so I'm going to draw Si here, and then O there, and O there. All right, so there's my skeleton structure showing 4 of the 16 valence electrons. So now I need to go in and assign the rest of those electrons, starting with my outer elements. I don't put dots on the central atom unless I don't have anywhere else to put them. All right, so I've got 2, 4, 6, 8. So there's 8, 10, 12, 14, 16. So there's all 16 electrons. I don't put any on my central atom because I don't have any left. All right, now next step then is to go and look at my central atom to see if I'm meeting the octet. In this case, I'm only showing 4 around my silicon atom. All right, so what I need to do is make more bonds. Okay, now hopefully at this point in your head you're like saying, okay, there's more than one way to satisfy the octet on the central atom. All right, we can do so with 2 double bonds, there and there. All right, so we still got 8, 8, 8. That's one way to do it. Okay, the other way is to go like this. I could go a triple bond on one side and leave the other with a single bond. All right, 2, 4, 6, 8, 8, and 8, still meeting my octet. Or I can do this just like this one, but just throw the triple bond on the other side. Okay, so in this situation, what we're running into is, unlike that nitrate polyatomic ion that we did on the last video, these are not all 3 the same thing. We have a difference, particularly in that we got 2 double bonds or a single and a triple. Now, these 2 are essentially the same thing, so we're not going to have to differentiate between which of these 2 is more likely. We need to differentiate between whether 2 double bonds is better or a single and a triple is better. Okay, so we've got to the point now where we've gone all the way through all 6 steps, but we still, at this point, we're not really sure if one is better than the others because they're not all the same thing. So the next step then is we're going to use formal charges, okay, to see if one of these structures is more likely than the other. All right, and the rule we're going to use is we're going to minimize formal charges when possible. All right, and notice that we come out neutral here too. This does not have a charge associated with it. We shouldn't have one here, okay? But if we can get 0 formal charges on all of our atoms, that's going to be our best option. So let's see what happens. All right, so valence minus formal electrons, right? Remember, each line counts as essentially 1 per atom, right? So I've got 2, 4, 6 formal electrons. Oxygen has 6. This is 6 minus 6, 0. So there's 0 formal charge here. This is the same thing, right? 6 minus 6, 0. And then silicon has 4. 1, 2, 3, 4. 4 minus 4, 0. All right. So that's a good sign right there that this structure is a pretty highly likely one. We got no formal charges to manage there, right? The valence and formal electrons are equal to each other for all three elements. Now, let's be sure that these others aren't equally likely. Okay? You're probably already spotting that they're not, but let's go through the exercise anyway. All right? So we got triple bond versus single bond. So again, I'm just going to draw little dots on the end of these to show that we're only counting one electron per atom, right? So we've got 1, 2, 3, 4, 5. So I've got 6 valence electrons in oxygen. And only 5 formal. That gives me a +1 charge, right? I've got 4 minus 4, 0 there. And then I've got 6 minus 1, 2, 3, 4, 5, 6, 7, minus 1. And of course, this would be minus 1 and +1 there. All right, so we had, based on the first 6 steps, we had 3 possible ways to draw this one, okay? But now I want you to then use formal charges, decide if one is more likely than the others. And the rule we use is we're going to minimize formal charges with our Lewis structure. Which of these structures has the least number of formal charges? That's going to be our 2 double bonds, 0, 0, and 0. Okay, so if asked to choose which one is best, you'd say, oh, this guy right here is our best one because there's no formal charges associated with it. All right? Now, you might be getting cocky. Oh, that's easy enough. Well, let's tackle this cyanate ion and let's see what formal charges does for us in this case. Okay, so we've got cyanate with a -1 charge. So we've got 6 valence electrons here with oxygen, plus 4 from the carbon, plus 5 from the nitrogen, plus 1 more because I have that negative charge. 6, 10, 16. Okay, now of those 3, which is going to be our central atom, the one with the lowest electronegativity, which using your periodic table you would find is carbon. I'm going to put carbon in the middle, and nitrogen there, and oxygen there. All right. Next step, put all my electrons in. So I've got 2, 4, 6, 8, 10, 12, 14, 16. I'm not putting any on my central atom because I've already got all 16 taken care of on my outer elements. All right. Next step down, I need to satisfy my octet for carbon. And you should be noticing that I can do that in 3 different ways. All right? So I can do so with 2 double bonds. That works. Okay? I can do so with a triple bond with oxygen and a single bond with nitrogen. Or I can do single bond with oxygen and a triple bond on nitrogen. Okay? 3 actually very different ways to draw this one. So I don't have like the nitrate where they're all the same, or even like the silicon dioxide with only one that's different. All 3 are unique ways to draw. All 3 meet all of these rules up through number 6. Okay? So, shoot. Well, which one's correct? Or are they all equally correct? Well, let's try formal charges. See where that gets us. Okay? So, in the case of our top one here, I've got 6 valence electrons in oxygen. 1, 2, 3, 4, 5, 6. Right? Let's put that up. 6 minus 6 is 0. That's good. I've got 1, 2, 3, 4 on the carbon. 4 minus 4, 0. And then on nitrogen, I've got 5 minus 6 equals -1. So that one comes out with 1 formal charge. Let's try this one. Triple bond on the oxygen. We're going to go 6 minus 5 equals plus 1. Okay, on the carbon, we got 4 minus 4, 0. And on the nitrogen, I've got 5 minus 7 plus, sorry, minus 2. Okay, so between these two, where the nitrogen has a minus 1 and the nitrogen has a minus 2, we'd probably say, well, probably not the best option here, right? That's more of a formal charge than that one is. Okay, but we haven't looked at this guy yet. All right, so on this oxygen here, we've got 6 minus 7, negative 1, 4 minus 4, 0, 5 minus 5, 0. Okay, so hold on. We did our formal charges, and the formal charges did help us in that we were able to eliminate this guy. That's probably our least likely of the three, but we've got one formal charge of minus 1 here, then one formal charge of minus 1 here. So is one of those better than the other, or are they equally likely? Answer is they're not equally likely. There's one more piece of information we can use from our periodic table. It's going to help us decide which one's better, and that's electronegativity. And essentially, electronegativity is attraction for electrons. So which one is most likely to get extra electrons, oxygen or nitrogen? And you would pick the one that has the higher electronegativity. So look into your periodic table. You're going to look at nitrogen, and you're going to look at oxygen. So they both, in this case, end up with a minus 1 charge with this structure or this structure. All right? You will choose the one that has the most likelihood of being negative, which would be oxygen because it has the higher electronegativity. So if you're given this scenario where formal charges only helps narrow it down, it doesn't give you one, you go to that final step there, electronegativity, which tells you you pick the one that's most likely to be negative. This is my best option because oxygen is more likely to end up with a negative 1 charge than is nitrogen. All right, and that's the extent of the complexity of drawing Lewis structures and being able to decide which one is best.